Today we will review in half an hour basics of magnetohydrodynamics. And just to make clear that we are on the same footing, everybody, I have to start from scratch, more or less, so that we are we know what we're talking about. From scratch, magnetohydrodynamics is a bit difficult task, so I will ask you to follow my suggestions. First of all, I just have to excuse if I won't use, well, they are mentioned in the notes, but if I won't use constants, because they are constants. So I will assume that all the constants we have won't affect the key equations, and so I won't spend time to put appropriate scaling in the equations. Okay, so this is one first big thing. Second thing is that I want to go to Maxwell equations as quickly as possible. So I will just start. Well, you have in the front page here, in the introductory notes, information about these constants and the role they play in terms of fluid that is charged. So electric currents are present, and because the fluid moves with a velocity u, then these electric currents produce a magnetic field. Everything in the general setting is unsteady, and with these motions you produce also magnetic fields. And this is the idea in the magnetic context. I'll rely on one equation that we need before Maxwell is the so-called Ohm's law, and is just relating the current J. So let's say that J is the electric current due to the motion of the electrons, electric current in the fluid, and we can decompose J in two terms. So one is just due to conduction, and the other one is due to advection. And as you know, the conduction is due to Ohm's law, which is, well, this is the only constant I mention here, just to make sure that we understand each other, the electric conductivity. And this is the electric field plus u, the velocity of the, say, classical fluid, so to speak, cross B, where B is the magnetic field. And from basic observations and conservation laws, we can derive the so-called, I would put a pre-Maxwell equation. And these are just relating possible sources or sinks first, sources or sinks effects. And the second set of equation is just relating the change in time of these key quantities, electric field and magnetic field. So remember, you have always to play tricks in your mind to remember things. So that's my way to remember those. First, thinking sources and sinks, and then second set, thinking the change in time of these quantities. So for the first is easy, because the divergence of an electric field is due to the presence of a charge, of an electron or a charge. So I'll call it rho E for the electron. And the second one is also easy, because I don't know if we may say, ongoing search for monopoles. So far, there have been no monopoles observed, and so we put a 0 there. And mind you, for the young ones, there are theories that are contemplating monopoles and have been developed to recast these Maxwell equations considering monopoles. So it works around. But these are the standard equations we refer to. And then we have to have the change in time of E, and the change in time of B. And as we know, one talks to the other. So dE dt is just the curl of B, and then this is contrasted by the current, and this is just minus the curl of A. So these are so-called Maxwell equations, and now we have to do some simplifications on these equations because we want to talk about the ideal case, ideal MHD, ideal magnetohydrodynamics. And so we have to do 3 simple assumptions to simplify our case, and further simplifications gives you the Kirchhoff's laws of electric circuits. So an exercise, I was given an exercise by somebody when I was really young, I mean your age. And so once you learn these equations, then please try your best to figure out the laws of electrostatics for a circuit, for electric circuits. And so that pushes you to understand what does it mean, divergence of E. You know, it pushes you to understand better what does it mean, a steady state, all these things. All right, so the first assumption, so assumptions, let's say assumptions for ideal MHD, magnetohydrodynamics. Okay, the first assumption is, I'd like to follow the order I put them down. First assumption is that we take a fluid to be electrically, I would say, sorry, it's better to say neutrally electrically charged. Okay, so that means that J due to conduction is 0. So immediately we have from Ohm's law that if that is 0, then there is a direct relationship between E and the field transported by the fluid, okay, over there. So we will have E from Ohm's law E will be minus U cross B. Okay, second assumption is steady condition for E. So if E is steady, that means dE dt is 0. And so from Maxwell, equation, we have dE dt 0, we have J equal the curl of B. Ampere's law. Okay? Third assumption is the consideration that perturbations, so to speak, due to magnetic fields are traveling much at a lower pace, so to speak, lower speed than the speed of light. And these perturbations are waves that propagate on magnetic fields. And you remember we mentioned that already when I mentioned Alphen, who proposed to Fermi a derivation of the velocity of the wave on a magnetic line based on derived from classical principles, so to speak. And Fermi had some doubts because he was thinking not of field lines but of particles. And so he was a little bit puzzled. Then he solved immediately the problem. But this analogy with the work of with the elastic bands that is rooted in the words of Faraday. Faraday wrote to Maxwell saying, you know, these field lines seem to vibrate like an elastic string. When you perturb a tight string, the vibrations persist for some time. And so this is one way to understand the behavior of magnetic field lines, because they do behave very similarly. So we have to introduce an Alphen speed, and say a velocity due to these propagations is related to the magnetic field. And this is putting constants once more here. We have rho E and mu 0. Mu is typically the permeability, magnetic permeability in free space. And so this V is assumed to be 1 over much smaller than the velocity of the speed of light, c. Okay. So this is the case, and under these assumptions we have also something important, that is the Lorentz force. And the Lorentz force, each field line is subject to this force, and this force is due to J and B, J cross B. So under these conditions we have this relation, and then enforced, and then the force, the Lorentz force given by J cross B. There is a mu somewhere. I will drop it. Okay, so for this we simplify this equation, or this equation can be rewritten. You see we have here, I'm sorry, I have to be consistent. I use the cross, and I try to remember to use the wedge. So the curl, so we have to put in place of E, U cross B here. And there is a minus and the minus, so we have Faraday's law. And Faraday's law says dB dt equal, we substitute, we have the curl, first of all, and then the curl works on that term from home, U cross B. And this is the law I referred to yesterday when we were talking about vortex motion. In deriving the equation of vortex motion at a certain point, you meet this form. I show you the statement about the Lagrangian derivative, which is a convective derivative. It combines time variation with space variation, and the time variation form is given there. So we are ready to have our set of equations. Now I write them down for the last time. The set of equations we deal with are the following. MHD consists of tackling the solution to this problem du dt. This is Navier-Stokes minus grad p. Then we have, I want to put for the very last time, the dissipative effects, so that we have the full equations in front of us. So I will consider nu, this viscosity. I mentioned that the viscosity terms have a second order derivatives on the velocity. And then I also mentioned the fact that we want to include forces that are conservative, and the Lorentz force is such one, and the Lorentz force given there, J cross B, over there, J cross B is this one. I want to put the wedge as much as I can so that you understand. I'm sorry, I get confused. I use the cross, but on the blackboard is bad to use it. All right, so this is, say, Navier-Stokes. Is Navier-Stokes in MHD, with this term, with the Lorentz force. Then we have vorticity, d omega. Let me write it in this way, d omega dt. And I want to write it in this way because I want to recall this structure. But I have also to take care of the viscosity terms now. So this would be the curl of u cross omega. Plus the same viscosity here, the second gradients come here, del 2 omega, and then I have to curl basically the contribution from u, so this is curl of J cross B. And finally, I have to take care of Faraday's law, but consistently with the classical fluid, I want to include, just to mention once, the role of dissipative effects. So I have to include the resistivity, dB dt equal curl of u cross B, and then plus resistive effect, del 2B. Fortunately for us, for me, I won't deal with this set of equations at all, but it's just nice to present this equation at least once. At least once. So this is the big business of solving these equations. You know, these are complicated enough, let alone the fact that the Navier-Stokes equations themselves are offer still challenging problems, is one of the major open problem of classical physics. Still, existence, regularity of solutions of Navier-Stokes, plus the effect of magnetic fields on that. Okay, so what we will do, as I mentioned a few times, we will do this, and this. And of course, when you do that, you have conserved quantities and topology frozen. Topology is frozen because there is no way, whatever is the structure, remember Cauchy solutions tell you that whatever is the complexity of the field, the topological complexity of the field at a position t0, it remains forever as long as the flow map is well-defined, it has an inverse, blah, blah, blah.
I have a question.
Yes?
So this set of equations, just to give us a picture, we have both the fluid, the velocity field, as well as magnetic field. That's why we just saw velocity, vorticity there, U cross omega, and we have some U cross B. So if the velocity and the field, magnetic field, for example, omega and B, they are just in the same direction, that will happen. The fluid, the lines of the fluid, field lines, can we just regard them exactly as the magnetic field lines?
If vorticity coincides with magnetic lines, this is your question? Is this? Well, you have, in general, it's hard to give, to answer. Pardon me? Yeah. So you may have in nature all sorts of, of possibilities. There are cases in which velocity and vorticity are aligned, which is a case very important because is a case where you have an excitement of complexity, so to speak, because you maximize helicity. We already know this. I didn't talk about magnetic helicity, but I already talked about kinetic helicity. So it's the integral of U dot omega. If U and omega are parallel, then of course you have maximum kinetic helicity. And but yes, sure, you can have a situation in which the field, for example, vorticity is aligned with B, or velocity is aligned with B.
A. Velocity parallel to A.
Also.
Yeah.
But velocity parallel to B is another interesting quantity.
Okay. So that means
because I might just mention it, but there are various definitions of helicities that include also the dot product of these fields.
So that means in MHD we have two sets of quantities. One set is kinetic ones, the other one the magnetic ones. For each group we have separate helicity, magnetic helicity and kinetic helicity.
Sure.
And if we ask them to talk to each other, we will have a so-called mutual helicity.
Cross helicity.
Yeah.
Yeah.
Yeah. Yes. Thanks.
Yes. Okay. Well, I want to indeed move to prove that we have a certain conservation laws under ideal MHD. So if I do this, I should put here an ideal disregarding these quantities. And I will prove two things. One is the conservation of flux, so to make a parallel with the conservation of circulation, of vortex circulation. And the other conservation law is conservation of magnetic helicity. So this is what I'll do in a moment. I start with the flux. Flux, similarly, yesterday we talked about localized structures like vortices, vortex tubes. We can equally think of having magnetic field lines that are highly localized. In the notes, you will see later on, I put a little picture, is barely visible, but it is visible, of of observations from satellite of plasma loops in the solar corona. And you see is a poor picture, small scale, whatever, black and white, but it's very clear that these plasma loops are well-defined loops in almost empty space. So it makes sense to think of magnetic fields that are highly localized, and they form tubes like vortex line form tubes in a fluid, in a classical fluid. So I will prove this conservation of flux. So let's say Alphen actually is like this. Alphen's conservation law for magnetic flux. So standardly, is evident here, so I didn't say anything, but if you compare these two equations, it's evident. That's why I put them down. Okay, so I won't talk about this, but you understand that there is evidently a very strong analogy between vortex dynamics and the transport of the magnetic field. So you would expect that similarly, in the ideal MHD case, the flux of that quantity, i.e. the field, through a surface, would be conserved. It's just natural to think about that. Anyway, we can, and let me add one more thing. As here I mentioned the Cauchy solutions that establish a class of equivalence between a field omega at a position initial and a field omega at the position t. And by this I denote, say, if at the positions at time 0, this is a knot, then this same knot is transported by the flow map to the same knot type K, different geometry, but it's the same knot type. Similarly, so this is due to Cauchy. Similarly, we can say that a knot that is made of field lines B at a certain time t0 is transported to a new shape, a new geometry, but the same knot at a later time. Okay, flux. Flux is the following for ideal MHD. This is a result due to Alphen. For ideal MHD flow, the magnetic flux let's call it phi. Phi in general is a function of t. Let's define it. Well, if we have a tube in mind, it's very easy to define it. So I will think of a tube. Of course, the definition of a flux is general. But if I think of a tube and I refer to one of these cross-section of this tube and I think of the field lines in this tube B, then I identify this sigma with the domain cross-section B dot nu. Nu is just a normal to any surface here, d2x. If I assume that these field lines are making up the cylindrical surface of this tube, for simplicity, then evidently I have no field lines going through by definition, by assumption, so this won't contribute to the flux, and I will have only the contribution through the cross-section sigma of the tube. So if we keep this example as a guideline for us, then we understand very well what is the flux, okay? Is the contribution of the field through a surface. Okay, this flux, the theorem is that this flux is conserved is conserved in the fluid, i.e. that the derivative with respect to time, Lagrangian derivative of phi t is 0, which means that phi is a constant of motion. Okay. So I will use again the transport theorem. That's why I introduced the transport theorem at the very beginning. Because once you do this, it's so easy, everything. And if you go to books, everybody has his own way to derive things, and you have to remember different types of derivation for each case. Whereas in our case, it's so simple. You call this theorem d dt of phi of t. So this is the integral sigma. You get in, you use transport theorem, right? So I have to remind you, maybe, transport theorem for a dynamical quantity, so to speak, for a vector. So this is just d dt of g vector, okay, in dv. This is the total derivative of g dt plus g dvu. And then I like to remind you of our definition of d dt, which is the partial derivative with respect to time plus the convective term acting on something. So here we have the convective term to read in d dt. In capital D, we have a contribution from this and the contribution from this that works on g. And here we have g times this. So this becomes db dt, the partial derivatives, times nu d2x plus, now you remember that we use to go from this, we left part of it in the volume and part of it we used divergence theorem to get the flux through. Let me step back because I want the young ones to follow. The change in time of this quantity is due to the change in time of the quantity inside a volume plus possible flux through the surface of the volume, right? The total change in time of a quantity is due to the change in time of a quantity inside the volume plus possible flux through the boundary of the volume. This is what the transport theorem tells you to do. So I have to think of this as made of this plus this that goes in here. So there is a divergence here. Divergence of GU, and I use the divergence theorem and I translate that into a surface theorem. Now, here I start from a volume, and I told you that I'm going to do part of it, this part, it will be done in terms of a surface, right? So here I start from a surface, and I have to take care of the flux through the boundary of the surface, which is the contour of the surface. Is the one-dimensional less case than this, if we are in R3. Okay, so we do this, and from here I told you we use this and this together gives the divergence of GU, the divergence of GU, and so we use in the volume, we use the divergent integral, and the divergence theorem gives us a flux through the surface. So the same here. We have the integral on the boundary of sigma, which is C B times the velocity u, because it's a flux, u cross dl, where L is the, is the contour of this surface. All right? Okay, so now we use here, from this term, dB dt, we have to go to the Faraday's equation. And so we have from Faraday's d phi dt is equal to integral of the curl of u cross b this is over sigma, of course, and as a nu d2x. And then we have to do, we just switch these terms. So there is a minus sign in front, minus circulation of u cross b dl. Okay? So first step is to go inside the integral with the total derivative, apply the transport theorem, use the divergence theorem to transform the volume integral into a surface integral. Here we transform the surface integral into a contour integral through this divergence theorem, and then we have a flux, and then this flux we just switch the position of these vectors in order to have a minus in front of here, and then we applied Faraday's equation here. All right, so now we get to the final step. We use Stokes. So we have the curl of this quantity through the surface. So we can reduce the sigma integral to a line integral. All right? So we reduce that. Stokes. Let me put it here. Stokes theorem means that we have a u cross b, and then this u cross b rotates, is a curl, rotates on the boundary of sigma c along the elementary length dl, and this is minus the other part, c u cross b dl, which evidently is 0. Again, flux theorem can be presented in many ways, and the effort that you pay to understand at the very beginning the transport theorem helps you in deriving many things. And actually, this is the idea behind so much work that was done in the 100 years ago or so. Okay. Then we are at the stage to prove conservation of magnetic helicity. Okay, so what is magnetic helicity? First of all, magnetic helicity. Magnetic helicity is defined by the integral, let's call it hm, function of t in general. And this integral, as by analogy, you may guess what is, because we saw this situation before, the analogy between vorticity and magnetic field, we have to have a field times its curl. So either we have a choice, right? We have a choice. I don't know anything. I think liberally, and I think, okay, I might have a B and then the curl of B. I do know what is the curl of B. Is hidden now, but we saw it. Ohm's law is Ohm's law. Ohm's law in the case where the conduction currents are zero. And the Ohm's law says, in that case, that B and J are related. Indeed, J is the curl of B. So I can construct an helicity that is J dot B. Here I'll introduce, and of course is used. It's called the electric helicity. I can't remember the name. Is used perfectly well. In this case, it's useful to refer to the magnetic context, and the magnetic context as an A times B, where A is the vector potential of B. This is in the domain of B, and before I forget, I will put here a W. And this W, it's better to say a few things. First of all, that B is defined in terms of A, that I choose a gauge for A, and I choose the Coulomb gauge. So that div A is equal to 0. So I fix the gauge in that fashion. And then it's still important to add one more thing. The domain of definition of B, so I take B such that B dot nu being the normal to the boundary of W, nu normal to dW, is 0. So on the boundary. In case we have field lines localized in space, like if it were a flux tube, then this is an easy condition to refer to, because you think that the field lines are parallel to the surface everywhere, and so we can think no flux through the surface, a very localized field, and so this condition tells you that the surface of this flux tube is a magnetic surface itself, right? So it's a material surface, and is made by magnetic field lines that are all tangent to this surface. So this is the definition and the conditions for magnetic helicity to be well defined. I remember is exactly the same as I did for the kinetic helicity. And now we want to prove that this quantity is conserved. So I told you proof of the helicity being conserved was done by two people, Voltier, 58, and Moreau in 61. In the magnetic case was Voltier, 58, and the paper remained unnoticed for some time. Actually, also the paper of Moreau remained unnoticed for some time. Conservation of magnetic helicity. Again, all these derivations are done in modern terms, and so I don't know exactly the derivation. I probably had a look at the time of the derivation of Volcher. I think Keith Moffat pointed out that there are a couple of, I wouldn't say, I don't know if mistakes or little points that are not quite right. Anyway, theorem. So this is a result of conservation of magnetic helicity. In ideal MHD, right. So this quantity HM is conserved in ideal MHD. So we have dH of t, in general dt, being 0, means h is constant in time. Okay, so first thing is that we have to prove. So proof, it goes like this. Let's uncurl Faraday's equation. And this is done by taking the A from it, the A dt. This is U cross B. And when we do this, you know, is if you curl it, if you take a curl, you do derivatives. If you uncurl, you have to have constants of integrations. So we have a constant of integration here that we will call it grad phi, a potential associated, or a gauge. So this grad phi, being a grad, has its curl 0. Okay? So we take this quantity to be like that. Now, because of the Coulomb condition, let's say on A, then evidently, if we take div A equals 0, then we have the solution for phi. Because div A equals 0, but A is has this phi in it. So we have immediately from this the del Q of phi equal minus grad of U cross B. Okay. This is a way to fix phi. All right. By using Faraday's, now by using Faraday's equation and the solenoidal condition for B and div B equals 0, we have to construct helicity d dt of something A dot B in our case. So Faraday's equation helps us to define dA dB. So we have dt. So we have A dot, actually the other way around. Faraday's helps us to define dB dt, the curl of U curl B. And then we have this grad on phi to take care of, and so we are there. And then I mentioned 2 days ago, probably, that or yesterday, that to prove a conservation of magnetic helicity, you need a little bit of algebra or vector analysis. So we'll make use of a vector identity. Use vector identity in the form that I write, because I want to keep track of what I wrote. So I will explicit it like this. A dot, I want to use that expression. So the curl of U cross B. And this is the div, sorry, this is, yes, is the div of A cross B cross U. And now use this vector identity I mentioned. You go to books, and you find that this can be written as A dot U B minus A dot B U. Okay, so right, we need the total derivative, and we are just with the partial derivative, so we have to play a little bit with these structures to say, thus, d dt of A dot B is equal to this quantity. We have to substitute this term here and extract this quantity. So we are with a div of what? Of phi. I'm putting together things plus A dot U. And then remember that there is div B equals 0. Okay. Now we're done, because when we see divergence of fields, we think of a flux. And if we think of a flux, we have to keep in mind the condition on B being having normal component 0 on the surface, on the bounding surface of the domain of definition of B. So that's why we are now close to say that indeed that quantity is 0. Okay, here, just to make sure that we understand each other, I should add since div, well, that was obvious, but div A B of U is equal to U dot grad AB. Okay? Because I want to construct this term. All right. Okay, so d dt of HM is equal to the integral. I go inside, this is a material volume. Sure, I use the same transport theorem, if you like, but now B is has no flux through the surface, so we have just the d3x. This is just V magnetic, let's say, of div. I put everything inside phi plus A times U, but here I have my B. And we said B has no component across the surface. So if I use divergence theorem, this gives you 0. So we are now at the stage where we have a very good parallel between a set of information and another set of information. And this parallel maybe bifurcates, goes in two directions, according to what we want to study and what we want to understand from nature. And the parallel is, we saw, is about, on one hand, very clear, vorticity and magnetic fields. On the other, I mentioned, you know, the helicity. When I talked about the helicity, you take a field times the curl of the field. So what about B and J? So you have this other helicity, the integral of B and its curl. So there is another parallel, a parallel between the electric current and vorticity. So we have two different analogies. So consistently with what is taught, analogies. Let's mention this. There is one analogy is called the so-called non-perfect analogy, and is between Euler's equation, and these are omega is given by the curl of U, and then we have the Helmholtz transport equation for omega, the curl of U cross omega, and finally helicity, kinetic helicity. Kinetic helicity is just the integral on this volume W of U dot omega. And then another set of equations, and these equations are ideal MHD equations, and these says B is given by the curl of A, and then we have the Faraday's law, dB dt equal the curl of U cross B, and finally helicity, magnetic helicity, integral over the magnetic domain of A dot B, d3x star. Okay, so you see very well the analogy. The problem is what I anticipated yesterday. The problem is that there is rather formal. Why? Because omega responds somehow to U as well. Omega is transported. It induces a velocity field through Biot-Savart law. But this velocity field, you remember the decomposition of the fields? The velocity field induced by omega is part of the field of motion, because the field of motion is made of three contributions. One, we call it, say, translation, deformation, so to speak, and rotation. So the rotation bit is due to omega, and then there is the rest. And so the fluid reacts on vorticity. So this is the nonlinearity hidden also clearly in Navier-Stokes, but is typical nonlinearity of Euler equations. Here is, in this sense, in the sense of reacting at something, there is no reaction on U. The fields are totally, they don't talk to each other. So you have a magnetic field that is transported by the fluid U. So in that sense, you cannot talk about a perfect analogy, although there are lots of things in common, because as we will see from this afternoon and tomorrow, we will see that Of course, we can give a topological interpretation of this quantity, which is exactly the same as this one. Actually, I will talk about the topological interpretation of this one, just because I think it's fun to change a little bit topic and stick to the magnetic fields to present things in that order. All right, but there is another analogy, and this is a so-called stricter analogy. So let's call it perfect analogy. Perfect analogy, and we like perfect things, and perfect things are nice, but sometimes we pay a price. You know, paradise is beautiful, is perfect, but you have to pay a price, a little price, to behave absolutely perfectly in all life, and so it's hard sometimes, and it's so hard that one to behave that way. You know, you have, I don't know, you have to be, for example, one way to behave that way is to be absolutely standing. You don't do anything for all your life. Probably you are perfect. You don't do absolutely nothing, anything. So perfect analogy in this case means that we have to be steady. Time does not exist. Steady. If we are in steady condition, then we have an analogy here that is perfect. So steady condition. Steady condition for Euler's equation means that we can reduce, we can rewrite them over there. We have let's say in steady conditions, then over there, this quantity is 0, right? Because d omega dt is 0. D omega dt is 0, so we can write from there Euler's equations become these get reduced to omega. Sorry, but I want to be consistent with what I wrote. Omega, the definition, curl of u. These become u cross omega. U cross omega, this is 0, right? If this is 0, then we have u cross omega equal a function grad, and we can call it h, is related to pressure. And then we have, as usual, the helicity, kinetic helicity. So this is just the integral u omega in helicity domain, in vorticity domain. Okay, and then we have MHD, and the MHD is that now steady condition. We can think of well, the definition of the electric current, curl of B, and then in static conditions, you have your notes. You can go back to the beginning when I wrote Navier-Stokes equation. You have a look, and you have to set the time variation equal to 0, and so you have on the two sides you have grad P minus grad P in a steady condition minus grad P plus the Lorentz force. The Lorentz force is J cross B. And all this is equal to 0. If all this is equal to 0, because there is no time variation, then we can rewrite this in this form. J cross B equal grad P. So this comes from Navier-Stokes in the MHD case. And then we have magnetic helicity. Now in this case, it's exactly satisfy this perfect analogy. So we have an analogy here not really between B and omega, but between the electric field and omega. So the analogy is omega corresponding to J, say, and U corresponds to B, and H would correspond to minus P. There is a minus somewhere I'm missing, and in the notes as well. Well, so this allows us to use this analogy to inspect properties. I already mentioned explicitly one case yesterday. The case, pardon me?
Maybe the velocity of a magnetic may be wrong. It should be J dot B.
You're looking for the other way around, perhaps? No. Ah, here. Thank you. J dot B. Yeah, you're right. Oh, done. Okay. I'd like to tell you something. I'd like to tell you this. This is an idea, is a strategy that I think is rooted in Arnold. And the strategy is the following.
Renzo,
Yeah?
that is G dot B, is that should be cross Olicity?
No, this is, well, I don't remember the name. Electric, do you remember the name of this quantity? J dot B? I don't remember the name. It's cross. I think it's wrong. It's a mistake. Current helicity. I'm sorry, is a mistake. It's not cross. Cross helicity is, yes, is U, is the velocity times the magnetic field. There are several helicities, and I made a mistake there. So this is current helicity, because it's associated with the electric current. Or before I said electric helicity, it's not. I was close, but. So which is the strategy? Let me give you an example first. I gave you already an example yesterday. The example is you build a tokamak, and you want a machine with the fields inside that are at least starting from the steady case, because you want a machine that is stable, functionally stable. So you don't want to start with something unsteady, right? So you want to start at least with something steady, hoping that there are no instability as you heat up the plasma. And the plasma is heated up by the interplay of electric and magnetic fields. Basically, magnetic fields are confining the plasma, are confining the electrically charged plasma. But these magnetic fields should be in a steady configuration. And the steady solution is given by the Grad-Shafranov equation, and is a torus, what you aim at, and so you look for a toroidal steady configuration of magnetic fields. This toroidal steady configuration is not a perfect a mathematical torus with a cross-section circular, but is a D shape. And that is the solution for the vortex ring case. Tomorrow I will show you some pictures. For the vortex ring case. So the two fields, the propagation of a vortex of a smoke ring, steadily propagating in the fluid. So it moves with a constant velocity. It doesn't decay, right? And the configuration of magnetic fields in a toroidal shape, so they are not perturbed, they stay there. They satisfy the same equation. The same equation. So you have a static condition that allows you to find the solution, for example here, and to transfer it by analogy to this set, or the other way around. So this is rather convenient, because remember of the non-perfect analogy. The non-perfect analogy has this devilish part in it. So what you can think of doing? Well, I can think of doing something like this. I work here, in this context. I start with the field B. I look for an equilibrium solution to the steady case in a B in equilibrium, which satisfies this context. Then I move to this case, and by analogy, I can identify a velocity, a vorticity, and I go there. So I can look for solutions in a steady state conditions and hoping that they will help me in general. And so this is just a strategy of working. So you look for a solution in a set, then this set in a steady state intersect this set of solution, you move into this set and you go back to the other problem. So this strategy has been used in many contexts, and one particular context is in searching for topologically complex configuration. So you can think, okay, I now for a moment, maybe a few decades, I'll leave aside the problem of vorticity. I move to magnetic fields. And on magnetic fields, the situation, because of this lack of interplay between U and B, I can think of modeling a magnetic field, see how it behaves. If it's knotted or linked, I can study its properties. And if some of these properties I find are steady, they stay there and there are solutions of the equation, then I can think, I can infer. The same is true for vorticity, and then eventually I consider the unsteady case, starting from the steady case. So this is the situation. So that's why I'm now moving consistently towards magnetic fields. We leave aside the story of vorticity. We consider magnetic fields, magnetic structures, magnetic knots, and relaxation of magnetic energy. Before doing this, I appeal again to your imagination and to Faraday's work. Faraday's worked on these magnetic fields experiments, and he noticed that they were behaving like elastic strings. Oh, by the way, I come up with a solution of my conundrum. I don't know at all if it, don't buy it, okay? It's not true. It's something I made up yesterday night, thinking of how on earth Fermi could confirm almost immediately the work of Alphen. And it came up my mind that the entry exam of Fermi at in Pisa, Scuola Normale di Pisa, the exam paper was several questions, but the first one, 2 students, not first-year students, two students who were applying to enter. You know, it's a small college, very small, but rather prestigious. So it's not ranking high in this table of rankings, you know, is down. But because of the college, it selects 50 students in the whole country per year. And the entry exam of Fermi was to derive from first principles the equation of an elastic string. That's why I thought it might be that the reason. An elastic string, you know, pulled tight and perturbed. And I'm not so sure, because I didn't check. I just remembered to have read somewhere that many years ago I read this. So I excuse you if please excuse me if I'm wrong with misquoting facts, but it's almost correct. That he was so talented that not only he re-derived correctly from first principle this equation of a vibrating string, but he found the solutions, new solutions. And when he was interviewed by the committee, the 3 professors or 4 professors in front of him said, oh, this is wonderful, you've done very well, etc., etc. So certainly you will pass and you will be one of our students. But, you know, we've been discussing, we cannot find out where exactly you studied these particular solutions. And he said, I didn't study these solutions in any place. What do you mean? Oh, well, I had some time, and I derived them. And so these solutions were derived on the spot by Enrico Fermi. Anyway, so perhaps this is the reason why he didn't believe Alpha in the first place. And when he left, we're talking many, many years later now, when he left to go back to Sweden, he probably recalled some of his interest in mechanics. All right, so this helps us to remember that flux tubes made by magnetic field lines behave like elastic bands. So we will keep our analogy with elastic bands in mind. I can even add, I never wrote it down, but I don't even know how, I did it many years ago. I presented a poster at a conference, and then it went lost. So, but it's a matter of really not like Fermi. It's a very simple example, simple exercise to do. If you go in the incompressible limit, you can prove that you can derive, so to speak, a modulus. It is like an elastic modulus, a shear module. And it's amazing. The order of magnitude with the due constants, etc., is very similar in the incompressible limit to the elastic case. So that you can think really of a flux tube that if you stretch it, it gets squeezed down as an elastic band because flux is conserved. Flux is conserved. So if you pull it, it goes down in cross-section, and the field intensity increases. But more than that is the action of Lorentz force. What does the Lorentz force on these magnetic field lines? Well, in your notes you have a rather elaborate calculation with appropriate orthogonal coordinates, which are not only circular cylindrical coordinates, but these coordinates, you will read it, are getting corrected by the amount of torsion that there is in the helix. So the usual cylindrical coordinates applied to the helical case are not quite correct because are not orthonormal. There are lots of papers with these coordinates. But you can prove that with a due correction due to the torsion of the helix, you get new coordinates, that these are giving you an orthonormal reference frame. Well, with these coordinates, you can work out the contribution of the force that is received from the magnetic field lines. So in order to do that, I won't do that in details, but I want to give you an idea of what we get. And what we get is absolutely easy and simple to remember, and is one way to remember it is to think of elastic bands. So playing with elastic bands is one way to understand. So imagine that you have your localized field in a tube. And now I take this field B inside this cylinder, and I want to write it. Let me check what I did in notation. I want to write it, I want to decompose this in possibly in a simple way so that I can do some analysis consistently with this geometry, with this cylindrical geometry. I would say, okay, first of all, I will decompose this field in the two elements. One is a contribution from Bm inside. So the field lines would wind up around the central line, and this is due to Bm. And then there is a contribution. You see these field lines are going up somewhere. Maybe I can use a different color so you see what I mean, a red one. These field lines, of course, mainly are longitudinal. This is the total field B, and the total field B will be is assumed to be decomposed in a meridional field and an axial field. The axial field is along this direction. Okay? So there is a meridional field BM like this combined with the axial field, and the axial field is prevalent on the meridional field. Then I want to have a little bit more general approach, and I would say that BM, let me use coordinates here, let's say cylindrical. I don't want to use, let's use this, Mercier coordinates are a little bit more general than cylindrical. R, E theta, which looks theta, let's say, and S. S is along the axis, R is, of course, in the cross-section, and theta is the azimuthal angle. Now, remember, these are not exactly the classical ones you use. I will put a little r there to denote the fact that there is a relationship between the standard theta and theta r, and the relationship is due to the fact that there is a contribution of torsion if the tube is twisted in space. So with these coordinates, I'll think of this decomposition as 0 along r, because I think of the field lines mainly along the axis. B theta is, of course, present in the meridional field, and I will choose some generality. I will choose B theta to depend indeed on r and theta, and eventually this theta can depend on s, because as you go inside, we want some complexity of this flux tube. We want a tube made like a cord, a rope, an alpine rope, or a rope that you use on the sea, on the boat. You look, you cut it through, and you see the cross-section. And the cross-section is made of threads, and these threads, they have a different helical pitch and a different configuration in space due to their different location. So I want to have some dependence on this in order to have a rope of field lines that are twisted inside the tube. And this is 0, and finally BA. And BA similarly will have no dependence on R, of course no dependence on theta, but along S will be a BS function of R. Okay, so this is the field. Now, with these coordinates and this field, we lose interest because we have to do some algebra. Why I want to do some algebra? Oh, I want to find out the force. And the force is the J cross B. But J is the curl of B. So given B, I can work out the force. Given the complexity of B, I can work out the force. So, all right, I won't do this because it is very boring. You have some details in the notes. It's a lot of calculations because, first of all, you have to have your operators in these coordinates. And then once you have your operators in these coordinates, you have to take care of the dependence of these various quantities on S, on theta, blah, blah, blah. So you do your calculations, you get an expression that is pretty complicated. But the crudest information, the crudest term, it's well known, is known since... what is the crudest term? Well, the the lowest order term is what is called a curvature term. So we have a Lorentz force, and the Lorentz force that acts on this tube, F, will have its three contributions of Fr, F theta, and Fs. But these are not very useful. So we can rearrange these three contributions into basically two contributions. F will be made by an F that is parallel to the axis of the tube, something, F of blah, 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 of the field, BA, BM, B theta, and BR, and an F perpendicular. These are two vectors. I can choose to rearrange F and the components in this fashion, a perpendicular term, and this perpendicular term will be a function of B theta and BR. But then I can drop all my sophisticated approach there to be very simple. To be so simple, say, okay, suppose this tube is a thin filament. Then can I say something about this force? Yes, of course. You can think of one field line. And if you consider one field line, so you drop down all this complicated approach, which I needed, because I needed later to do some more sophisticated analysis. That's why I mention it. But if you want just to understand the behavior of a field line, you may say that the field line orthogonal contribution goes approximately like a curvature, the local curvature, the curvature of the axis of your tube, or the curvature of the field line, times the normal direction if I choose a Freinet-Serret system on the line. Okay, I have my field line B. I can choose to use the unit tangent, and with the unit tangent I will have to identify a normal direction. Now, as usual, you have to put a Freinet frame somewhere like this, and so you have a normal direction and the binormal direction. Tangent, normal, and binormal. You remember what we did the very first lecture. If x denotes the position, this is a fixed reference frame. If x denotes the position of a point on a line, then we have, I can recall you the Freinet system. Freinet reference system is given by T, N, and B. And T is just defined as dx. I take x, a curve given by x function of s only. This is s, coordinate somewhere. And then I have dx, ds. If s is arc length, this contribution has a unit length. So this is the definition of the unit tangent. And then, just because I wrote this equation, I recall you the Freinet-Serret equation. We will use it later. I won't mention them now, but I will make use of Freinet-Serret equations in a moment. How these triad, tangent, normal, and binormal change along the curve. So how they change it. Because I want to take the derivative with respect to arc length of the tangent, of the normal, and the binormal, and these are the equations that control this change. For the moment, that's enough, but I want to say this. This is my simple-minded equation. I have a field line, and it moves according to the local curvature along the normal. What does it mean? It means that you take your rubber band, you stretch it, and when it's stretched, you release it. Ideally, you see that this rubber band will shrink. So it will be subject to a motion, so to speak, along the unit principle of this idealized circular situation, configuration, and it will shrink towards the center of curvature. And the intensity with which it will move is given by the local curvature. The more is bent, the faster will move if it were a velocity. I said we stretch a band, and you say, well, Renzo, you mentioned the analogy with elastic bands, but an elastic band on a table doesn't move at all. Aha, this is the little trick, and the little trick is this. Imagine, now this is the very last step of your analogy, imagine that the magnetic field natural length, the natural length of a magnetic field, imagine that is 0. So whatever is your length, it will be subject to a shrinking flow, is like a rubber band that has 0 natural length. So whatever is your new rubber band will be always subject to tension. Okay? So it's a rubber band that whatever is its length is always under tension. And so it will shrink. It will shrink exactly as a real rubber band of a given length. So you deform it from its natural length, and you will feel the tension and the shrinking. And the mathematicians call this a shrinking flow acting on the band. And now I stop with this little problem. You take a rubber band that is always shrinking because it's always subject to a tension like a magnetic field line, and you think, what about if it is a knot? A loose knot that is made of magnetic lines. It won't stay loose. It will shrink always, because we said this is the force acting on each point of this physical field line. It will shrink, but is knotted. It cannot shrink to 0 because the flux is conserved. Okay, we start from there. We take a break of 20 minutes, 15, yeah, okay.